For the experimental part, one thing that I'm going to ask is, like, keep in context that these experiments were run 4 years ago. So even though the paper got accepted and published much later, the data is from a time when training took a lot longer and state of the art was different from what we have now. So that's one of the reasons, for example, why ImageNet is not in this set of experiments. But also keep in mind that the goal is not, for this paper, is not to find new state of the art on a data set. It's not to show a new learner method, but to show, which is the kind of the point with most distillation papers, to show that you can shortcut the learning process, that you can make things, that you can simplify, right? And so before you simplify, you complicate, which is kind of the trajectory, right? You complicate by building an ensemble, you simplify by distilling. So that's the principle. CNNs, we know, on computer vision problems do these things very well. So that the first one, which is deep incremental boosting, part of my lack of imagination for naming things, starts in the same way as AdaBoost. You train a model, usually a very simple one, and we'll see why in a second, on your data set. You find the mistakes, but then you start the second round and all subsequent rounds by doing transfer learning first between the previous round. So you copy exactly what you had, you still change the data set, you still reweight that, and you add capacity to the network. That usually means add a layer or a couple of layers, or however you want to structure it. That's sort of part of the hyperparameters. Yeah?
How is it different from XGBoost, where you just add another tree, where your additional model is just one more tree and keep the rest constant?
It's very similar. Like, that's kind of where the inspiration came from. I don't actually cite XGBoost in here because I don't know, like the timing was a little bit weird.
What is the deep part about it?
The deep part is like mostly because you can only really do this on deep networks, right? Because if you do a number of rounds, you end up with a very deep network, right? And so the idea is that that last layer is adding capacity to learn the corrections from the previous layer, based on the reweighting as well, right? So you're doing a sort of double emphasis on, I want to make this correction. The weighting mechanism stays the same as AdaBoost for combining the classifiers. So that's the first version. Second version. So then, this is an example of how a network evolves. Like, you start with 4 layers, you copy them, do 5, copy, do 6, and you copy, right? This was also, I think, part of the review request, like, we need to visualize it. Okay. Very unimaginative. There is, okay, so this, yeah, okay, it's not in here. There's a second version. I keep forgetting the timing of my own papers, which is fun. But the second version is called Boosted Residual Networks. It's basically the same thing, except you add a skip layer. By adding the skip layer, you make the fact that you're learning corrections even more explicit. So it's a tiny tweak. So okay, you're not going to see experiments with boosted residual networks in this paper, but I think there's another paper that summarizes a lot of these things that actually has all the experiments in it. So is this actually new work? So despite what is sometimes led to believe and patent filings that you will see, distillation is not the new thing, right? This has been done in signal processing for so many years. It's called meta models, but the principle is exactly the same, right? You have something that's distinctive. I think I've said it when I was talking about the first Hinton paper. It's absolutely fine. I think that it doesn't detract anything from the contributions that have been made afterwards, because it's still all very valuable, and meta models aren't directly applicable to the distillation work, but it means that it's not completely novel. So also Hinton already mentions that you can approximate an ensemble with a neural net, right? We've seen this in the first paper, where they create this pseudo training set. I'm not going to go over it again, but the point that they make is that the distillation is not a regular. So, and I'm going to go over the differences in a second, because we do have some differences. So, distilling in deep learning, this is just a summarization of Hinton's paper and a couple of other things that we actually already spoke about, like when we talk about adversarial examples, actually simplifying gets rid of that overfitting. So I just saw a broken reference. Okay, this is probably not the final version of the paper then. So when we distill deep networks, we start from, I'm going to try and use as little rigor as possible. But let's say you have two spaces, right? These are big space of, this is all your possible set of inputs and all your possible set of outputs, right? So this is literally all the possible combinations you could have. So in a case for a CNN that takes continuous valued inputs, these two spaces are in. This one isn't, right? Because it's a set of classes. The first function that we have is a function that goes from, these are all the possible versions that actually happen, to their corresponding labels, right? So you call these X and Y. Okay, this is the function that we can never observe. We call it like nature, or whatever you want. Then we have a training set, which we usually accept that it's going to be, I'm going to call it X bar and Y bar, that we try to learn. So this is what we learn with, I think I call it F bar. Right? So this is our model. And we know why learning using this proposition works, because this is a subset of this, and this is a subset of this. Now, however, what then happens is you have a bit of a distortion where there are some errors, right? This is your mapped outputs, right? So this part here are the errors that your classifier makes. So then, if we try and map this function and try and learn it, which we call f hat x, we're